So here we go. Starts recording. Okay. So I know some of you have been doing the homework, which is great. And one of the first few problems on the homework is to learn how to classify numbers. So we're interested in classifying numbers. That's the first thing we're going to talk about. What are the numbers that we know of? And there are four major ones, four major categories for numbers. So the first one are what are called the natural numbers. AKA, they're called like the counting numbers, right? Because these are numbers that we've learned throughout the years, and we usually learn them through counting. So what are they? They are 1, 2, 3, dot, 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 so on and so forth. Those are our natural numbers, counting numbers. And there's a symbolic way. So one thing about mathematicians that they like to do is they don't like to write a lot of stuff. Like they don't like to write a lot of words. They like to simplify the amount of words that they write as much as possible. And how do we do that? Well, we utilize symbols that represent a whole phrase or expression. So instead of writing natural numbers all the time, they decided to write it this way. So it's an N indicating natural, and there's like an extra little dash underneath there. So this N here is a symbol for the natural numbers. So whenever you see this N, this is the symbol for natural numbers. Okay, so again, kind of self-explanatory what natural numbers are. These are things that you learn when you're in kindergarten, first grade. There's 3 blocks, there's 5 apples, that kind of thing. Right? Oh, no problem, Emil, no problem. Yes, David, the natty numbers. That's the first time I've ever heard of that, but that's a good way to put it. However, there's more to numbers than just 1, 2, 3, 4, 5, right? A million, 1,000. There's more than just these whole numbers. There's also called whole numbers. So there's a lot of names for this. They're also whole numbers. So natural numbers are called whole numbers, aka counting numbers, aka natty numbers. But what other numbers are there besides natural? Does anybody know? What numbers are missing from this list?
Imaginary?
Whoa, 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 whoa. Imaginary. Of course they're not here. And of course they do exist. But for now, we're not going to deal with imaginary numbers. We're going to deal with strictly real numbers, quote unquote. So yeah, some people here talked about real numbers and negative numbers. So we are missing negative whole numbers. And in particular, we're missing 0 as well. So then the extension of the natural numbers are called the integers.
What do you mean?
Now, the integers include all of the natural numbers. They include all of the, so they include natural numbers plus 0 and all negative version of natural numbers.
So 0 is not a natural number?
That's a good question. That's a very good question. So maybe to you it does seem natural to include zero in the natural number group. But to many people back in the day, zero didn't even exist. The concept of zero was not introduced until an Arabian mathematician came up with it, came up with this idea of zero. So I understand how it makes sense for zero to be included, but um, for now, one, two, three, and so on are considered natural numbers. This idea of zero is special. It's not something to this zero. This just the concept of zero is a very unique concept. So no, it is not considered a natural number, sadly. Um, so the integers, the symbol for the integers is something that you wouldn't expect. There is no I. It's like a Z. There's an extra slash. So when you see this symbol with the Z, and I think I forget. There's a reason why it's a Z instead of an I, and that it's I believe because it might have been German. I don't know if it might be German or some other European language that represents integers are represented using Z, using a name that starts with the letter Z. But I'm not familiar with that. Right. So
Sure.
yeah.
Sorry, quick question. So the Z symbol, whatever, is that something that we'd have to like remember? Or like,
For like if you're saying you have to remember this for a test,
yeah.
not necessarily. Like again, this is more of review.
Oh, right. All
It's
right.
more of a review,
Okay.
but this is just like an added piece of information that could be useful. Uh, because what we're doing here is trying to give you a very structural and organized fashion of understanding what numbers are and making sure that everyone understands the classification of numbers, the way that we categorize numbers. So natural numbers are things that we've seen. Integers are an extension of these natural numbers. So then you'll start to see how everything is kind of related with one another. The natural numbers are one set of numbers. That's another understanding you need to consider is what are called sets, S-E-T-S. And a set is just a group of things. In mathematics, of course, we care about sets of numbers. So when we have a set, and that's why I wrote this little curly braces here, these curly braces indicate this is a set, or in other words, a group. So the natural numbers is a group of numbers that are of this kind, one, two, three, they're whole numbers. The integers include this set, but now they extend towards the negative, quote unquote, direction and include the number in between the positive and negative numbers, which is exactly zero. So then we can call this set, sorry, this set of the integers are 0, 1, 2, 3, dot, dot, dot. As you can tell, so this is one thing about mathematics that's cool, I believe, in my opinion, is that this dot, dot, dot is so powerful. In a way, we're saying, hey, this goes on forever, but since we don't have forever to write this out, we just say, hey, you get the idea. So it's like we're just saying 1, 2, 3, so on and so forth. 1, 2, 3, so on and so forth, 0, comma, -1, -2, so on and so forth. So do you see how in this region here, this portion here is really the natural numbers? And you see why now having this symbol is useful because I'm not going to be writing natural numbers out every single time now. Now I have a specific symbol that represents the natural numbers. And that's what makes mathematics a little bit easier to express yourself in because of these symbols have meaning to them. And we don't have to write out all the words out every single time. We just use symbols. So it's very symbolic in nature. Okay, so does that make sense? So now the integers include all the natural numbers, include its negative version, and include 0. right? Okay. So, of course, we haven't included all the possible numbers that exist. We started with natural, now we go to integers, but now we're missing numbers, right? We're missing those numbers in between the whole numbers. And what are those numbers that are in between those whole numbers? They're known as what?
Decimal numbers?
So there are decimals, but in particular, we don't call them decimal numbers or decimals. We call them rational numbers. So these are the rationals. Now, what are rational numbers? They're numbers that can be expressed as fractions. So numbers that are expressed as fractions. And the symbol for this one is pretty interesting. It's a Q. Now, this is when things get a little bit more abstract, because now the question is, how do you express all of the rational numbers? So you see how we have this little dot, dot, dot symbolism for the previous two sets of numbers, which makes sense to use. But here now it's a little bit more complicated. How do we apply rational, like how do we express a rational number? Well, I'm gonna write it this way. So the set of rational numbers are all numbers that can be written as a fraction. And how is that possible? So they're all numbers. I'm gonna call numbers x. All numbers x such that x is equal to p over q, where p and q are integers. Now, this kind of writing is not so standard, but I want you to start to understand that to express something mathematically, right, requires precision. There's a lot of precise statements that are being made. So if you have a number that you can express as a fraction of integers, that's a rational number. So an example, right? Example, how do you represent 5? Is 5 a rational number? It is. Why is it a rational number? Because I can rewrite it as 5 over 1, right? And 5 over 1 are what? Integers, right? Does Emil have a question? Hand raised.
Oh, that was an accident. Sorry about that.
Oh, yeah, no problem. And then, for example, how about -4? How can you express -4 as a rational number?
-4 by 1.
-4 by 1, or what? 4 over -1. Same thing. How about 0?
I don't think you could express 0 as a fraction.
Oh, you can't. So 0 is not a rational number?
You can, but every number you put on the fraction, it came out 0.
So, okay, so Jalen says 5 over 0. So is 5 divided by 0 equal to 0?
No.
No. So be careful, guys.
So it
5 over 0 is undefined. We're going to be talking about this later. But whenever you divide by a 0, it's undefined. So actually 0 is no good. But if you flip that around, 0 divided by 5 is 0. And very good, Tyler. 0 over anything. 0 over 1,000,000 or 1,000. They're all zeros. So 0 can be expressed more than one way. And actually, other numbers can be expressed more than one way too, right? Isn't this 10 over 2? Isn't that also 5? Isn't this like 16 over -4? Isn't that also -4? So you start to see that you can express a number in more than one way for rational numbers. And then there's a connection, right, between fractions and decimals. I should write it as rationals. So what's the relationship between rational and decimals? Well, a rational number has a terminating decimal. Example. 1/4 is the same thing as what? As in decimals? .25. So you see, by terminating, I mean there's an ending. It stops. 1/4, 0.25, stop. Or what? A rational number may also does anybody know what else a rational number could have in terms of its decimal expansion? Does it always have to be terminating? Does the decimal expansion of a rational number always end?
No, it can I forgot the word for it, but it's like when you put the little hat over the number, like when
Yeah.
like 1/3 is like 0.33333. It just keeps going.
Right. So Tyler says it's repeating. That's right. Has a infinitely repeating decimal expansion. And does anybody have an example of a rational number whose decimal expansion repeats itself? So I think you mentioned it, Devin. 0.33333. What is that? What fraction represents that decimal expression?
1 over, it's not 1/3, is it?
It is
1/3?
1/3.
Yeah.
That's right. That's right. 1/3 is 0.333 ... so on and so forth. Or you can write it as 0.3 with the bar over it, indicating that 3 is repeated throughout. So these are rational numbers. These numbers are numbers whose decimal expansion stops somewhere, or a decimal expansion that has a repeated number. Right, Valerie, good. 10 over 3 is 3.3333 repeating. And there's many, there's an infinite number of these. Jerry, that's right, 1/9 is 0.1111 repeated. Okay, so we talked about natural numbers, integers, and rational numbers. Do you see that the rational numbers include all of the integers? So the integers include all the natural numbers. The rational numbers include all of the integers. Now, and if you start to see, right, you can write this in a number line. This number line will be very useful. So we have 0, we have 1, we have 2, we have 3. We have -1, we have -2, we have -3, and this goes on forever, right? From the right to the left. When we include 1, 2, 3, so on and so forth, these are the natural numbers. When we include the 0 and the -1, -2, -3, we talk about these as a general idea. When we talk about now the numbers in between, like the 1/2, the 3/2, the -1/2, the -1/4, right? We're including all these fractions now. That includes all of the rational numbers. So now my question is, are we missing any numbers? Do the rationals include all the numbers that exist on the number line?
No.
No. So what are we missing if we don't include all of them? What are the numbers that just completely are not included in either in the rational set of numbers? So yes, imaginary, unreal. People start talking about the unreal numbers. So again, like I said, we're not going to be considering the imaginary numbers in this class. So you don't have to worry about the imaginary numbers. But good, I'm glad you guys know their existence, which is kind of an oxymoron, right? They're imaginary, yet they exist. Yes. But what are the other numbers that are real, but are not rationals? They are not integers. They are not whole numbers. So there's numbers here that we're missing. And that's right, Tyler. Those are the numbers that are irrational. So you can call this like 3. I'm gonna call this 3 star. These are the irrational numbers. And this IR, right? This prefix is like saying not. So irrational numbers are simply numbers that are not rational. That's all they are. So if you're not rational, what does that mean? If you're
That
an irrational,
a
yes,
number cannot be turned into a fraction that
right.
contains integers.
It is a number. It is a number that cannot be expressed as a fraction of integers. So that's interesting. So there are numbers that cannot be expressed as integers. Huh. Can you give me an example of a number that cannot be expressed as an integer?
Pi, like 3.14.
Whoa. Pi. It's a
Yeah,
very nice number.
thank you. Is that
Pi
wrong?
is a very nice number. It's beautiful. It's 3 point what? Do you know it? 3.14?
Yeah, that's all I know up to be
That's all
honest.
you know too? Does anyone else know anything else? People, there's a contest, right? People have contests of how many digits they can actually memorize because this goes on forever. 3.16, 3.15. I think it's 3.1415926.
Don't
And
they
this goes
also
on
have a
forever.
contest to discover like what's the next digit in pi? Like there's like a race or something to figure out how far
Yeah,
it can go. Yeah.
right. So this goes on forever. It's just that, like it's like saying what is the 1,000th digit? What is the 1,000,000th digit of pi? What is the billionth digit of pi? Like it becomes like a contest. It becomes like a race. People care about these things. As you like, even if you think about it, like, wait, what? People care about this? Yeah, there's some people out there that really care about what is the the trillionth digit of pi. But the idea is that this number goes on forever, and it's a non-repeating decimal. So irrational numbers are numbers whose decimal expansion is non-terminating and non-repeating. So their decimal expansion is non-terminating and non-repeating. So that's important. They don't repeat. And they don't stop.
Professor, I have a question.
Yes.
Can you consider the same for 1/3 though? Because 1/3 as a decimal is like 0.3333. Wouldn't you say that's also non-repeating?
So be careful. irrational numbers are non-terminating and non-repeating. Irrational numbers are terminating or repeating infinitely many times. So 0.33333 describes exactly a
Oh, I
number.
mixed it up. Yeah, I got you.
Yeah.
Yeah, my bad,
So,
my bad.
so this is a number that indeed does repeat, but this number pi doesn't. It's called a random. It's random. Do irrational numbers have a symbol? You can create one, but for now, you don't have to worry about the symbol for irrational numbers. One way to describe it is you have to learn a little bit more about sets. And so because the set of irrational numbers, I mean, the set of rational numbers is given by Q, there's something called the complement of a set. And this is just a little more abstract understanding of what sets are, set theory. So the complement of a set is the set of things that are not in the set that you're talking about. So if you're referring to the complement of the rational numbers, you're actually you're talking about all the numbers that are not rational. So this is one way to indicate the symbol for irrational numbers. This is basically saying, hey, do you guys remember the rational number set? Well, yeah, take everything that's not in it. That's the irrational numbers. But there's no exact like one single letter that represents irrational numbers, not that I know of. And I have a question. What about I? I is an imaginary unit. And like I said, you don't have to worry about I. I is like another, like lives in another realm. We're not going to be in that realm. We're going to be in the realm of real numbers. So again, this is cool stuff, right, guys? So we talk about natural numbers, integers, rational numbers, and then associated with those rational numbers are called irrational numbers. And the cool thing is, if you connect or if you put together all of the rational numbers with all the irrational numbers together, you have what's called the real numbers. So this stuff sounds simple, but it's actually very profound. It's actually very profound. Real numbers. So when you talk about a real number, you're talking about a number that's either irrational or rational. So this includes all rational and irrational numbers. And there is a symbol for this. The symbol is the letter R with an additional dash, a line. So real numbers include all rational and irrational numbers all together. And so when you draw a number line, everything on the number line is either going to be irrational or rational, which means that they're going to be a real number. And I want to give you another example of an irrational number, which would be the square root of 2. The square root of 2 is irrational. If you put this in your calculator and you find the square root of 2, it's 1.414213 and this goes on forever and ever and ever and ever and ever and ever, doesn't stop. And there's no pattern to it. It's also random. But for example, what about the square root of 49? Is that an irrational number? Is the square root of 49 irrational? It's not irrational.
Oh,
It's rational. Not only is it rational, what else is it? It's an integer.
natural number.
And it's a natural number, right? So you see how now you can categorize a number. Now you say, oh, 7. So the square root of 49 is, this is rational. But if you say it's rational, that, and in particular, what kind of rational number is it? It's an integer. And in particular, it's a natural number. So it crosses all of the It checks all those boxes. It's a rational, integer, and natural number. Okay. Okay, great. And one way to visualize this, maybe it might help. So to visualize the classification of numbers, what's one way of doing so? So there's a lot of visualization that can help. So the way I look at it, the way some people look at it, is like a set of numbers that look like this. So we started with what? We started with the natural numbers, right? So these are all the sets of numbers here. So these are 1, 2, 3, a million, 1,000, right? And then the next range or the next group that extends these natural numbers are the integers. These include 0, negatives, all the negatives of the natural numbers. And then what extends this even further are all of the rational numbers. So these rationals include all the integers, which includes all of the natural numbers. And what includes everything altogether?
Real
are the
number.
Real numbers. So this is one visualization of it. The natural numbers are inside the integers. The integers are also inside the rationals, and the rationals are within the real number set. That's one way to see how everything fits into the other categorization. Okay. Okay. Emil, do you have another question, or is that just a hand raised from before?
Oh, my bad. Yeah, that was
Oh,
from
no. It's okay. All right. Great. Great. Now we understand real numbers, rational numbers. Okay. So and I kind of touched upon this a little bit, but I want to talk about sets a bit more. And what's a set? Sets
the grouping
it's
of numbers.
yeah, is a collection. It's a collection of things, objects. In particular, in mathematics, we talk about numbers. And there's a very systematic way of expressing what we can do with sets. So we have, let's see. Right, we have ways to express sets. So for example, I'm gonna give you an example first and then we'll talk about it. I can say A is a set. How do I denote sets? So we're gonna use curly braces to indicate a set. So when we say, for example, A includes the set 1, 2, 3, A is a set that includes the numbers 1, 2, 3. So this set has 3 elements, or these set, I should use the word here, elements. A is a set that contains 3 numbers, and these 3 numbers are 1, 2, and 3. Now, let's say I want to say 2 belongs to A. How do I say that mathematically? We use this symbol. 2 is an element of A. So what this means that 2 is an element of set A, or 2 belongs to set A. So the key word here, the phrase is an element of or belongs to. So whenever you see this little symbol here, looks like an E, this means belongs to. Yes, Emil, did you make another question?
You literally just answered it.
What did I answer?
I was confused as to what the E.
Yeah.
Yeah. Yeah.
So again, a lot of this stuff, right? Okay, so one thing that makes mathematics difficult is the language barrier. Mathematics is a language, and to many, they describe it as a universal language. So like if I go to any part of the world and I write this on a chalkboard, people would understand what I'm saying. For those of them who understand mathematics, so mathematics really goes through supersedes the language barriers that exist. The problem is that it's in itself a language, right? So it takes some time to understand what these symbols mean. And once you have the understanding of the symbols, then you're able to process the symbols a lot better. So this is nothing crazy. This is literally saying 2 belongs to A. 2 is an element of A. So we're going to be using this to indicate if something belongs or does not belong to a set. So for example, I should say, so 2 belongs to A, right? In this example. But then you would say, what if something does not belong to A? You would say 4 does not belong to A. You can just literally write the same symbol, but just a slash through it. And that tells you that 4 is not an element of A. So you can say this means does not belong to. Okay. All right. So now let's get a little more complex with this. Okay. So we're gonna talk about something that's called the set builder notation. I think some of you have seen this before. Set builder notation. Set builder notation. So what if I call a set example? What if I call the set, for example, and I use this so this looks kind of scary, doesn't it? You're like, wait, what in the world? But can anyone tell me, given the symbols here, does anybody see, or can anyone see something that they've seen before?
X belongs to R.
What does R represent?
I think real numbers.
Correct. So what are you saying? So this is saying X is a real number, right?
Yeah.
Okay, so X is a real number. That's pretty important. Okay. So X is a real number, and then does anybody else? Oh, Tyler said X belongs to all real numbers less than 20. Perfect. So look what we said. X is a real number, and at the same time, X is a number less than 20. So then what does B contain? B is a set of numbers that are real that happen to be less than 20. So if you really want to explain this whole thing out, and what is this notation here? What is this little bar dash, this dash represent? This represents literally the words such that. So I can literally literally say this. These symbols here represent a whole mathematical expression. In particular, you can express this as a mathematical statement. So you can say B is the set. Why do I say it's the set? Because remember what we said, the curly braces indicates set. So the moment you see curly braces, that's a set, a group. So B is the set of all real numbers such that they are less than 20. So we just broke down this whole expression here in words. The better you become at doing that, the easier all of this will become. And now look what we can do. This is called the set builder notation. And now we can graph this, can't we? Do you guys know how to graph set B on the number line?
Would we have to find out what x equals to first?
Well, x is anything less than 20. So I want to graph, what does that mean? X less than 20. So on the number line, right, we got 0, 1. Actually, let me make this by 5. 5, 10, 15, 20. This is -5, -10, -15, so on and so forth, right? So to indicate what this represents graphically, I'm saying, hey, x represents all of the real numbers that happen to be less than 20. So how do I draw that? How do I express that? Well, yeah, we do that open close circle thing, right, Valerie? So we say, hey, 20 is the indicated number here that we have. And I want to shade. Remember, people shade it. So we're going to shade everything to the left of 20. So graphically speaking, this represents exactly what I just expressed in symbols. So in symbols or in symbolic set builder notation, I'm literally saying, hey, shade everything to the left of 20. And we're doing this open circle because we don't include 20. 20 is not included. That's why. 20 is not included in set B. Because 20 is not less than 20. 20 equals 20. So 20 does not satisfy this condition inside here. Is everyone with me? Does this make sense?
So yeah, it makes sense, but what, well, you have to shade the other part. Like in this case, you shaded all the other parts except 20, or is that just you trying to like explain to us? Because like I get the rest, like it's pretty straightforward.
Yeah, so you're asking why do we not shade the 20?
No, like I'm saying in this case, if you were to graph, let's say another set builder notation, you would shade the other numbers that correlate to what the set equals to, like how you did for that, let's say -15.
Yeah, it can change, right? So I'll give you another example. But before we do that, I want to show you another way to express this set. So we can express a set as a set builder notation. We can express a set as a graph, and we can also express a set using interval notation. So what's the interval notation for this? Well, that's why graphing it helps. So graphing it, what did I just graph? Or what did I shade? I shaded everything to the left of 20. This goes on to what? This goes on to this left end. If you go all the way to the left, you're approaching what's called negative infinity. If you approach all the way to the right, you approach what's called positive infinity, right? That's what we do. Okay, so the shading part, Valerie, the shading of it, in a way, many people shade it differently, right? Some people I know, they do this. They do like this thing here. They put the arrows. It's not necessary. You can do that, but it's not necessary. I already understand that if you're shading it all the way, that it's approaching negative infinity. And if you shade it all the way to the right, it's approaching positive infinity. But if you want to put the arrows, that's also all right. Now, because of this, because I can visualize now what is the shadedness, what portion of the number line I'm shading and what portion I'm not shading, then it helps me to just say, you know what, instead of shading stuff, I can just write it more compactly as an interval. And what are the interval? The interval utilizes two endpoints. pardon me, and what's the endpoints here? Well, the endpoints to the left, right? We have no endpoint really. We're just approaching negative infinity. So I can write this as negative infinity. And then this is the leftmost endpoint of my interval. So this is the leftmost endpoint of interval. And the rightmost endpoint of my interval happens to be 20. Because I don't shade at anything beyond 20. 20 is like kind of like that marking point. And then we call that our rightmost endpoint, right? And because we don't include 20 in our shaded portion, we have to use a parentheses. So I'll give you another example where it's going to be not a open circle. So this is open circle, but a closed circle. And then if you see that difference, then you'll see why we have to use a different notation for a closed circle. Okay, does that make sense? So this interval notation here represents this graphical representation of the set builder notation. So what you're gonna have to start becoming comfortable with is going from set builder to graphical to interval notation, back and forth, back and forth, back and forth. Being able to go from this representation of a set to graphing it to interval notation and back and forth. Again, these mean the exact same thing. They're just expressed differently. That's another thing about mathematics. You can express one thing in 3 different ways, 5 different ways. So let me give you another example. So what if I call the set C, for example, the set of all real numbers such that x is less than 5 but greater than or equal to -4. So what am I saying here? I am saying that C represents all real numbers such that these real numbers are between -4 and 5. So see, x is less than 5, but x is also bigger than or equal to -4. So if I'm going to graph this, if I graph this, what do I get? -4 somewhere here. +5 is somewhere to the right of it, right? You got 0 in between if you need a reference point. Then I know that 5 and -4 are part of these endpoints. I know I have to shade everything in between it because that's what x is in between. However, I don't include 5 because why? X is strictly less than 5. So since it's strictly less than, I don't include. But this symbol here, less than or equal to, x could equal -4. And so henceforth, I shade. So close circle, because x is greater than or equal to -4. And this is open circle because x is less than 5. Does this make sense? Now, what would be the interval notation for this set? -4, 5. So correct. So -4 and 5 are obviously the endpoints. 5 is the rightmost endpoint. -4 is the leftmost endpoint. 5 is not included, so I use a open parentheses. So parentheses for intervals indicate open circle. For -4, I have a closed circle. So what denotes a closed circle in interval notation? It's a square bracket. So this square bracket, indicates at -4 is included. The parentheses indicates that 5 is not included in the set. Okay. So we're understanding now how to go from set builder, graphing, interval, interval, graphing, set builder.
Kinda.
Sorry about that, guys. My internet stinks, so I was kicked out. All right. So what if I give you the interval notation, such as this one here? Let's say -1 to infinity. What would be the graph? What would that look like? And what would the set builder notation look like? Who can tell me what the graph would look like? Yes, anyone. Who David, do you want to offer your idea?
Yeah.
Mhm.
So -1 would be closed circle,
Correct.
and you would shade everything until infinity. So
Right.
I
You
guess
just
till the
shade
end of it.
everything to the right. Good. So that's how you graph it. So that's pretty straightforward. Now, what would be the set builder notation? So,
Would it
so
be
for set builder,
that sorry,
say it again.
X is I'm guessing it's a real number.
Right. And how do you say that it's a real number? We use that little
X
symbol, right?
XE real number
Mhm.
such that
Such that
X is greater than -1, greater than or equal to.
right, greater than or equal to, and we also don't forget the curly braces around.
Oh yeah.
So this here represents exactly what you just explained to me in terms of graphing it, which explains exactly what the interval notation is. So all in all, these three things here, they represent the same thing. Represents the same exact thing, which is what? The shaded region. You can express it as a shaded region. You can express it as interval. You can express it as set builder notation, or you can express it in words. It's the set of all real numbers that happen to be greater than or equal to 1. Done. Good. Good stuff. Does anybody have any questions about sets? This is good. I like sets. Now, maybe somebody can ask, but okay, that's cool. That's cool. So, but what happens? Say that again. Oh, sorry. Yes, you're right. -1. You're right. -1. Thank you. Thank you. This should be a negative one, not a one. Should be a negative one. Now, the interesting thing about sets is that you can also have sets that don't contain anything. And you're like, wait, what? How is that possible? Well, there's things that are called the empty set, also known as, AKA, the null set. The empty set is just literally a curly braces with nothing in it. So the symbol for, if you have a curly braces with nothing in it, that's the empty set. Or you can also use like a circle with a slash through it to indicate the null set. So it's literally the set that has nothing in it. And you might be like, but why do we care about sets that are this way? Well, it is useful. In particular, we're going to talk about what are called the intersection and union of sets. Yeah, so Sierra, this is exactly where I'm going to go into. So for example, the union and intersection of sets. You guys have interesting questions. What is the difference between the null being different from undefined? Wow. So first of all, undefined comes from the idea that you are not able to give a definite answer. That's why it's undefined. It's not defined. So when you say 5 divided by 0 is undefined, it's undefined because there's no definite answer. The null set just means that there's nothing inside of the set. The set contains nothing. So it's kind of two different concepts. Though they might feel like they're the same, it's two different concepts. When you say 5 divided by 0, we're not saying, are we saying that the answer is in the empty set, or in this null set? That's a good point. But they're kind of two separate fields. They're, in a way, they're kind of two separate fields. An unknowing of risk was absolute nothingness. Yeah, that's a good one way to put it. Emil, you have a question?
Yes, sir. I don't really understand what you mean by union and intersection of sets. Like, does that hold any correlation with the concept of empty set? Or like,
Yeah. So I haven't even explained what the union intersection is. That's exactly where I'm going next.
Oh, all right.
Yeah.
Good.
So far all we've done is understand a bit more what sets are, right? And in particular, we're talking about sets of numbers because this is a math class, but you can literally talk about sets of other things. It doesn't have to be just numbers. That's my point. Like there's an idea of what's called set theory. And particularly when we talk about like computer programming and computer science, there's a lot of set theory involved, but not just in computer science, in other realms, subject fields of study as well. But this is a little bit more abstract stuff. But what is a union of sets and what is the intersection of sets? So we can explain this very simply. I'm going to use the same exact set that I started with, 1, 2, 3. And let's say I have a set 4, 5, 6. So I created, so look, you can just create sets just out of nowhere. I just created one. I did it. And that's very underrated. People underrate how powerful you can be, particularly in mathematics. You can create stuff. It's not so black and white. It's not just so textbooky. That's the way we present mathematics, right? Through textbooks, but math is much more than just reading it through a textbook. It's very creative. But so okay, so we have two sets, A and B. A has 1, 2, 3 in it. B has 4, 5, 6 in it. What's a union? What do we think what union is? A union is just uniting two sets together. So how do we express that? We use a symbol called U. This means union. So this is saying, hey, take everything that's in A and take everything that's in B and just create one single set. So 1, 2, 3, 4, 5, 6. This is the union of A and B. I put together, and it kind of feels natural to do this, right? 1, 2, 3, 4, 5, 6, just put them all together. So the union of sets includes everything that is in both sets. That's it. That's the union. That's it. And then let's say I do something like this, right? Let's say I do C. The union, the C is what? 3, 4, 5, for example. What would be the union of A and C together? What if I take the union of A and the union of C? What's the result?
You'd have 3 like repeating, like would you have to write it down twice?
No, you don't.
It's gonna be 1, 2, 3, 4, 5.
That's it.
Wait,
That's
but
another
doesn't
thing.
C
So,
have 3 also?
say it again.
Yeah, but bracket C has 3 and so does A, so you wouldn't have to like write it down like twice.
But why would that change anything? Why would adding 3 twice help you understand what's the union of A and C?
I mean,
So what you have to realize is, because you're right, it's repeated, right? It's repeated. 3 is repeated, but that does not, repeating it twice does not indicate that anything different from just repeating it once. You understand?
yeah, I understand.
So that's just part of the set building writing process. You just include 3 once, even though it's repeated. So that's the union of A and C, right? But now let's talk about intersection. So what's the intersection? So let's look at that. The intersection is just given by upside down U. Now, what does the intersection do, you guys think? What does that indicate? So union includes everything. What does the intersection include? David says red pills, blue pills. That's the union, but what's the intersection? The intersection includes everything. Yeah, that's right, Devin. Only what they have in common. So what's the common thing between A and B? No, A and B. Not A and C. Right, Maria, nothing. So how do you express nothingness in sets? You say it's what? It's empty. So this is where emptiness comes from. This is where the empty set is necessary, right? Because you may have a set or 2 sets that have nothing in common. So how do you say that they're nothing in common? You say the set is empty. So the intersection is the set of all common elements. And then when you say, what is the intersection of A and C? Then you can say, hey, A and C, the only thing that's common is 3. So this is called just a set 3. And this is an example of what's called a singleton set. So the sets that have only one thing in it are called singleton sets. It's a set that contains only one element. Does this make sense? Is does,
Sir,
does
yes,
this
sir.
now say that again?
I said yes, it does.
Okay, good. It's supposed to like kind of be like, oh, like it's a natural way of going about things, right? It's like, oh, it makes sense if you take a union of sets, you just combine everything together. If you take the intersection, then you only find the things that's in common. So that's good. Okay. So now, how is this utilized? Why do I care about this? Is because now I can mix it all up now. Now I can mix all these things up. Now, what if I say this? What if I say I have the set of all real numbers such that x is bigger than 1, and I want to union the set of all real numbers such that x is less than -1. Do you see now? Can you express this? This is set builder notation. Can you express this as a graph? Graphing it? What would be the graph of this? So now I have two sets and I want to union them together. So when I union them, I just include both of them together. So how would this set look like when we graph it? Anybody? Just take each set individually. Did all of this union of sets scare you guys off?
Just this example.
Take it step by step. Take this guy here and just do that for now. Open circle on 1, Jalen. Okay. So we got open circle on 1. And then what? Where do we shade it? It says greater than 1, right? So we're going to shade it all the way to the right. So that's like, you can call this A, for example. If you want to call this is my set A. And then what's my next set? Call it some other thing. Call it B. So that's going to be everything to the left of -1. And again, I don't include either the -1 or the +1 because they're all both open circles. So that's it. That is the union. That's the union. And then what would be the interval notation for this? Well, what's the interval notation for the first shaded portion? It's everything from what? -infinity all the way to -1. And what about the second portion here? It's everything from 1 to infinity, right? But then what are we doing with those intervals? We're doing what? Union. So this union can be also utilized in the interval notation. Does that make sense? And then what would happen? What would happen now if I take these same two examples and I take the intersection of them? What is the result of intersecting these two sets?
The empty one.
Right. There's nothing. The null set, that's right. I have nothing in common. There's no overlap of the shaded regions. So there's nothing in common, so we say it's empty. And there's nothing to graph, and there's nothing to say about the interval notation for this. Make sense? Let me give you another example. What if I have the set of all real numbers such that x is less than or equal to 2, and the intersection of the set of all real numbers such that x is greater than or equal to 0. Now, what would be the graph of this? So remember, we care about the intersection, not the union. So again, treat these two things as different sets for now. So what's the set A indicate? Everything less than or equal to 2. So I'm going to be using closed circle, shade. And for B, I'm going to use everything bigger than or equal to 0, right? But what's overlapping? What is the overlap portion of this graph? So this is A. Sorry. This is A and this is B. Right, that's very good, guys. It's in between, right? So everything in between 0 and 2, this is the union. So this represents the intersection, pardon me. This is the intersection of A and B. Because that's where we overlap. And then what would be the interval notation for this? We care about the overlap. So we can rewrite this later as builder notation. But what would be the overlap notation, interval notation for this? It's only from 0 to 2. So 0 is the leftmost endpoint. 2 is the rightmost endpoint. Square bracket, because I include both 0 and 2. So the intersection of this set with this set produces this overlap and can be written as the interval notation here. And if you really want to make this into one single set builder notation, you can just write this as x between 0 and 2 this way. So intersection and union are ways to are two operations that can be applied to sets. Okay. And so we are finished with